Once again, welcome back to the next lesson in AC circuits. Today, we will discuss about the flow of AC through a pure inductor. An inductor means a coil made up of a large number of insulated turns of copper wire or any conducting wires. The condition is that the turns are insulated from each other so that the current has to go through the coil in a turned fashion, that is in a spiral way. So these type of coils are called inductors. If an alternating EMF is applied to an inductor, then the current passing through that inductor will be continuously changing, because the alternating EMF means the applied voltage is changing in magnitude and direction. So the resulting current will be also changing in magnitude and direction. As the current passes through the inductor, a magnetic field will be produced around it. So the inductor is placed in the field produced by its own current. Hence, a particular amount of magnetic flux will be linked with the inductor. As the current passing through the inductor changes, the magnetic flux associated with the inductor also changes. This change in magnetic flux induces an EMF in the inductor, and this EMF will oppose the change in magnetic flux. Actually, the magnetic flux is changed because of the change in applied voltage. So this induced EMF will oppose the applied EMF, and hence this EMF is called back EMF, and the phenomenon is called self-induction. Actually, self-induction is a general phenomenon. It happens in almost all AC circuits, but it will be more pronounced in the case of an inductor. For any AC circuits, there will be a non-zero inductance. The phenomenon of induction of back EMF in a circuit due to the variation of current passing through the same circuit is called self-induction. So an inductor or a coil can be called as a self-inductor, or it will oppose the change in current passing through it. Now we consider a pure inductor. Pure means that inductor has no resistance. That inductor has an inductance L, but the resistance of that coil is zero. Practically, a pure inductor is impossible, because for any coil there will be a finite resistance. But here, for the theoretical treatment, we are discussing a pure inductor, and this discussion is valid for an inductor to which the resistance is much negligible than the inductive reactance. The term inductive reactance will be discussed in this chapter. So we consider an AC voltage, say E equal to E0 sin omega t, be applied to a pure inductor of inductance L. Now, if I is the instantaneous current in the circuit, then the back EMF induced in the circuit will be E or epsilon. In some textbooks you can see epsilon. Here E is equal to minus L into di by dt, where L is called the inductance of the coil, and I is the instantaneous value of the current, and T is the time. In order that the current may just flow through it, that is, if the current flows through it, then we can surely say that the applied EMF E should be, at a minimum, it should be equal and opposite to the induced back EMF. Here we assume that the inductance is pure. The inductor is pure means there are no resistances in the circuit. So the full applied EMF is used for overcoming the back EMF. Therefore, the applied EMF capital E will be equal and opposite to the back EMF small e. Therefore, E is equal to minus of small e, or it implies the applied EMF is E0 sin omega t, minus of small e is minus L into di by dt. So minus into minus, it becomes plus. Our aim is to find the current passing through that circuit. So we get di by dt is equal to E0 by L into sin omega t, or integral di is equal to E0 by L, it is a constant, can be taken out, integral sin omega t dt. Now integrating this expression, we get integral di is equal to the current I is equal to E0 by L into integral of sin omega t is minus cos omega t by omega. Minus cos omega t by omega, plus there will be a constant of integration because this integral is an indefinite integral. Actually, in some textbooks, this constant of integration will not be shown. This is not necessary, but in some other textbooks, you can see this constant of integration. In any way, this will be 0, where k is called constant of integration. Now, k is 0 because as the average value of current I in an AC circuit is 0, and the average value of cos omega t is also 0. So, when we take the average value of this equation on both sides, we get average value of I is equal to minus E0 by omega L into average value of cos omega t plus average value of k. So, we get average value of k is equal to 0. As k is a constant, if average value of a constant is equal to 0 means that constant is equal to 0. So, we get k is equal to 0. So, the current passing through the circuit is I is equal to minus E0 by omega L cos omega t, that is equal to E0 by omega L into minus of cos omega t can be written as sin omega t minus pi by 2. And that is equal to I is equal to this E0 by omega L is a constant, can be called as some I0. So, I equal to I0 sin omega t minus pi by 2, where I0 is equal to E0 by omega L, or that is equal to E0 by XL. It is the peak value of current in the circuit. Now, from equation 1 and 2, from equation 1, E equal to E0 sin omega t, and in equation 2, the resulting current I equal to I0 sin omega t minus pi by 2. We see that the current I is lagging behind the applied EMF by a phase of pi by 2. Or in another way, we can say that the applied EMF is leading ahead of the current by a phase of pi by 2. However, the back EMF is opposite to the applied EMF. So, back EMF and opposite and applied EMF are out of phase, or they have a phase difference of 180 degree or pi. Therefore, back EMF lags the current by a phase of pi by 2, but applied EMF leads the current by a phase of pi by 2. So that the phase difference between applied and back EMF is pi. The important point is applied EMF and the resulting current. So the applied EMF and resulting current, when we discuss the phase difference, we can see that the current is lagging by a phase of pi by 2 behind the applied EMF. Now the variation of applied EMF E and the current I with respect to time, here omega t is shown in the first graph. We can see this red line represents the E equal to E0 sin omega t with E0 with the maximum peak value, and the blue line represents I equal to I0 sin omega t minus pi by 2, which is the resulting current. So we can see here the voltage is 0 and voltage is increasing from 0 to maximum, but current is increasing from 0 to maximum after an angle of pi by 2, or after a phase of pi by 2. So current follows the voltage after a phase of pi by 2, or we say voltage is leading the current by a phase of pi by 2. And the phasor diagram, which is used for representing the phase difference and also the magnitude of these two time varying quantities, voltage and current. Here the voltage, peak value of voltage E0 is represented by a unit of 5, and the peak value of current I0 is represented by a unit of 3. And in this picture, E is leading the current I by a phase of pi, because the angle between these two phases are 90 degree, and in the anti-clockwise sense, the voltage E0 is leading the current I by a phase of pi by 2. So this is called a phasor diagram. Now a new term introduced in this lesson is inductive reactance XL, which is equal to omega L or 2 pi FL, where omega is the angular frequency, F is the frequency of AC, and L is the inductance of the coil. This quantity is called the inductive reactance of the inductor. We have seen that the peak value of current I0 equal to the peak value of applied EMF E0 divided by XL. And converting from peak to RMS value, if peak value is divided by root 2, we get RMS value. So I0 by root 2 is equal to E0 by root 2 by XL. Or we can say that the RMS value of current IRMS is equal to RMS value of applied EMF ERMS divided by XL. So these formulae are similar to the Ohm's law. I is equal to V by R, and in the place of R the quantity XL comes. So it is the resistance offered by an inductor against the flow of AC. If the inductive reactance is very high, it means that current will be very low, and unit of XL is ohm, and unit of L is Henry. It is measured in Henry. Now one of the application of this inductive reactance is in the case of choke, or called choke coils. An inductor offers an opposition against the flow of AC. So this can be used to control the current in an AC circuit. For example, if we use an inductor in series with a bulb connected to an AC supply, if the inductance of the coil is very high, then the voltage available to the bulb will be very small, and the bulb will glow only with a very small brightness. So this inductor increases the inductive reactance of the circuit so that the current through the circuit is controlled. So the inductance used for this purpose is called choke coil. It offers a high inductive reactance for high frequency AC. And for controlling low frequency AC, we can use a choke coil of high inductance. If inductance L is very high, then omega L will be very high even for small frequency. So small frequency AC and high frequency AC, both of them can be controlled by using choke coils. And we are familiar that current in AC or DC, they can be controlled by using resistances. But while using resistance, a part of energy is lost in the form of heat. But the advantage of choke coil is, in using choke coil, we can control the current in an AC circuit without any wastage of energy. So it is one of the important advantage of choke coil. Nowadays, for controlling AC currents, we are using choke coils, and resistances are being replaced by choke coils. But what is the case for DC? In the case of DC, frequency is 0. So the reactance becomes 0 because XL is equal to omega L, which will be 0. So the inductor has nothing to do with a DC circuit. It is just a short circuit for DC. Short means there is no resistance or reactance offered by an inductor towards the flow of DC. So an inductance is an easy path for DC, but it is a difficult path for AC. So direct currents cannot be controlled by using inductors. So DC can be controlled only by using resistances. It is one of the limitation of DC, because when current is controlled by using resistances, there will be always a heat loss by Joule's heating effect, H is equal to I square RT. But in the case of AC, the current can be controlled without that heat loss. So after watching this video, you should be able to answer the questions like, what is the phase relationship between the voltage and current when AC passes through a pure inductor? What is meant by inductive reactance and what is its unit? Now, inductor is a difficult path for high frequency AC and it is a short circuit for DC. Explain this statement. And this type of inductors can also be used in filter circuits to filter the AC and to pass the DC to the output. What is meant by choke and mention its advantage over resistors. Thank you for watching this video.